What if an object that astronomers have been tracking for nearly 30 years, calculating its orbit, cataloging it as a routine near-Earth asteroid, turned out to be something completely different all along? Right now, an object called 1998 SH2 is orbiting our Sun on a 4.5-year path. And according to new research led by scientists at NASA's Jet Propulsion Laboratory, it was never an asteroid at all. For 28 years, it fooled the entire astronomical community, hiding its true identity in plain sight. And the only reason we finally know the truth is because in August 2025, it simply failed to show up where every single calculation said it should be. And let's start with the numbers, because they're what make this discovery genuinely remarkable, without any exaggeration needed. 1998 SH2 was first discovered in 1998, and for nearly 3 decades, astronomers tracked it as a routine near-Earth asteroid. It has a diameter of approximately 383 meters, roughly the size of a skyscraper. On August 28, 2025, it passed safely within about 2 million miles, or 3 million kilometers, of Earth during its 412-year orbit around the Sun. That's roughly 8 times the distance from Earth to the Moon, but when NASA's Deep Space Network planetary radar system pointed its giant antennas toward the exact region of space where 1998 SH2 was predicted to appear, based on decades of orbital data, there was absolutely nothing there. The object had vanished. Here's the part of this story that almost no coverage explains properly, and it's the part that matters most. This isn't just a case of a misidentified space rock. The deviation wasn't small. When astronomers finally recovered the object using optical telescopes in Brazil, they found it a whopping 153 arc-seconds away from where it should have been. To put that in perspective, that's roughly 190 kilometers off course. In orbital mechanics terms, that's a massive positional error. And when the research team calculated the statistical significance of that deviation, they found it was 19 standard deviations away from the gravity-only predicted position. That number is so astronomically large, it rules out measurement error as an explanation. Something was actively pushing this object off its predicted path. I'm the host here at Today Latest Analysis, and every claim in this video comes from actual published research, including NASA's official findings and a peer-reviewed paper in the journal Nature Astronomy, not exaggerated headlines or unverified speculation. Subscribe now and turn on notifications, because this discovery has massive implications for planetary defense, and there's more coming. Let's start from the beginning, because to understand why this deception lasted nearly 30 years, you need to understand what astronomers look for when they classify an object in the first place. For most of the history of astronomy, the line between asteroids and comets has seemed fairly clear. Asteroids are rocky bodies that orbit the Sun, while comets are icy bodies that, when warmed by sunlight, develop a glowing coma of gas and dust and often a spectacular tail stretching millions of miles. That's what the textbooks say, anyway. But in reality, that line has always been blurrier than most people realize. Some objects simply don't produce enough gas and dust to form a visible coma or tail, even if they are, in fact, comets at their core. These objects look like asteroids through every telescope we point at them. They behave like asteroids in almost every way. Except for one crucial detail, their orbits don't quite work. 1998 SH2 was first discovered in 1998, and from that point, through 2016, astronomers tracked its orbit around the Sun with precision. It completed 2 full solar orbits during that period, each taking roughly 4.5 years, and its path seemed perfectly consistent with what you'd expect from a typical asteroid. Then, for 9 years, from 2016 to 2025, ground-based telescopes didn't observe it again. That gap turned out to be critical, because during those 9 years, something was slowly, imperceptibly altering its trajectory. Here's the second layer of this story, the part that makes this feel like a detective case rather than a routine astronomical observation. When the 2025 close approach came, the research team, led by Davide Farnocchia, a navigation engineer with NASA's Center for Near-Earth Object Studies at JPL, had calculated exactly where 1998 SH2 should appear, using data from previous orbits. They factored in everything they knew: the gravity of the Sun, the gravity of the planets, everything that could possibly influence the path of a rocky asteroid. And then they pointed the 70-meter DSS-14 radar antenna at the Goldstone Observatory, part of NASA's Deep Space Network, toward that precise point in the sky. Nothing. Not a trace. This is where the story takes its first genuinely surprising turn. The team didn't immediately assume the object was a comet. Initially, they suspected equipment malfunction. But when optical telescopes also failed to find the object where it should have been, and then finally spotted it far off course, they knew something else was going on. The deviation was eventually measured at roughly 190 kilometers from its predicted position. As the research team put it in their Nature Astronomy paper, the non-gravitational perturbations affecting the motion of 1998 SH2 weren't compatible with the object being an asteroid. That's scientific language for a bombshell. The object wasn't following the rules asteroids are supposed to follow. So what was pushing it? The answer is outgassing, the same mechanism that drives comets. When a comet approaches close to the sun, the heat turns ice mixed with rocky material into gas. The gas escapes from beneath the surface, and like a tiny natural rocket engine, it generates a small but persistent thrust that pushes the object off its purely gravitational path. In regular comets, this outgassing is dramatic enough to produce a bright coma and a long, visible tail. But when an object produces gas in much smaller quantities, its tail and coma may be too faint for most observatories to detect. That's exactly what happened with 1998 SH2. It was outgassing, just barely enough to alter its orbit over time, but not nearly enough to give itself away as a comet through conventional observations. For 28 years, that tiny, persistent thrust had been silently pushing 1998 SH2 off course, and nobody noticed, because nobody was looking closely enough to catch it. It's worth pausing here to explain what scientists actually mean by non-gravitational perturbations, because it's a phrase that gets thrown around without much explanation. Gravity is the force we expect to govern the motion of every object in the solar system. The sun's gravity, the planet's gravity, the moon's gravity, all of it is predictable with extraordinary precision. When an object deviates from that purely gravitational path, something else must be producing a force. In the case of 1998 SH2, the research team considered the Yarkovsky effect, a subtle phenomenon where an asteroid's rotation causes it to emit heat asymmetrically, generating a tiny push. But the detected non-gravitational perturbations were 10 times larger than the maximum possible acceleration compatible with the Yarkovsky effect for an object of this size. That discrepancy immediately ruled out the standard explanation for asteroid orbital drift and pointed squarely toward outgassing. To confirm their theory, the research team turned to some of the most powerful telescopes on Earth. They enlisted astronomers at the 3.6-meter Canada-France-Hawaii telescope near the summit of Mauna Kea in Hawaii, the 1.5-meter European Southern Observatory's Danish telescope in La Silla, Chile, and the 8.2-meter Very Large Telescope on Cerro Paranal, also in Chile. Using these observatories, they stacked multiple long-exposure images of 1998 SH2, combining faint signals over time to pull detail out of the background noise. And there it was, a faint but clear cometary tail extending about 20 arc-seconds away from the nucleus. The images showed something else fascinating. The majority of the dust grains in the tail appeared to be around 400 micrometers across, roughly the size of coarse sand, and the dust seemed to have been released between August 29 and September 7th of 2025, during and immediately after the object's closest approach to Earth. But here's the detail that tells scientists the most about what's happening inside this object. The activity actually peaked several weeks after its perihelion, the point in its orbit closest to the Sun. That timing suggests the ice driving the outgassing was probably buried deep beneath the object's surface, taking time to warm up and release gas even after the object had begun moving away from the Sun. Following this discovery, the object received a new provisional comet designation, P1998 SH2, alongside its original asteroid catalog number. It's now officially classified as a comet. But not just any comet, a dark comet. Here's the part of this story that has the biggest implications, and it's the part that planetary defense scientists are genuinely concerned about. The study, published in Nature Astronomy on July 15, 2026, led by Farnokia and confirmed by JPL in a press release dated July 16, 2026, represents the first time the cometary nature of an object was predicted based on its orbital behavior alone, and then confirmed by direct imaging. That's a major first in astronomy, but it also exposes a blind spot in how we track potentially hazardous objects. Every impact probability calculation for near-Earth objects depends on orbital models that assume purely gravitational motion. An object that is slowly thrust off course by outgassing introduces an error term those models will never detect. And over the course of 2 solar orbits, that error can compound into a positional uncertainty large enough to place the object well outside where any telescope expects to find it. That's exactly what happened with 1998 SH2. It spent 27 years in planetary defense catalogs as a routine asteroid, and all that time, it was quietly drifting off its predicted path because of outgassing that no one could see. Davide Farnokia, the lead author, put it directly. After we measured the non-gravitational perturbations affecting the motion of 1998 SH2 and recognized they weren't compatible with the object being an asteroid, we suspected the object could be an active comet. Olivier Hainaut, an astronomer at the European Southern Observatory and co-author of the study, added, "The images we collected from these observatories showed a weak but clear tail, thus confirming that 1998 SH2 is, in fact, a comet." So here's what this discovery actually means, once you separate the confirmed findings from the speculation. 1998 SH2 is not an asteroid. It never was. It's a dark comet, a class of objects first identified in 2016, of which astronomers have now found about a dozen. Dark comets are objects that follow paths suggesting they're releasing gas, yet they show no obvious coma, tail, or visible outgassing. They look like asteroids. They're cataloged as asteroids, but they behave like comets. And the implications for planetary defense are serious. There's a high chance that many more objects currently classified as asteroids could actually be comets. These objects can change orbits and acceleration in ways that complicate tracking efforts. If an object is slowly drifting off course because of outgassing, and we don't know it's happening because the outgassing is too faint to see, then our predictions of where that object will be in the future and whether it might pose a threat to Earth could be significantly wrong. It's worth being direct about what this doesn't mean. 1998 SH2 poses no threat to Earth. Its close approach in August 2025 passed safely at about 2 million miles, roughly 8 times the distance to the Moon. This isn't a warning about an imminent impact. What it is a warning about our assumptions. For nearly 30 years, every astronomer who looked at 1998 SH2 assumed it was an asteroid because it looked like one. It didn't have a tail. It didn't have a coma. It didn't have any of the visual hallmarks of a comet. And yet, underneath that perfectly ordinary exterior, it was outgassing all along, quietly pushing itself off course with every orbit. The research team's analysis of observations collected since the object's discovery in 1998 allowed them to determine that the perturbations to 1998 SH2's motion were caused by the sun-heating ice mixed with rocky material, turning that ice into gas. With regular comets, this activity forms a trademark bright tail and coma. But when an object produces gas and dust in much smaller quantities, its tail and coma may not be detectable to most observatories. That's the definition of a dark comet, an object that's actively outgassing but doing it so quietly that it escapes detection. This discovery also connects to a broader mystery in astronomy. Since the first dark comet was identified in 2016, astronomers have found about a dozen more. The research suggests that many of these objects could simply be comets with tails too faint to detect with conventional observations. In other words, the number of dark comets in our solar system might be far larger than we currently realize. And if that's true, then the number of objects whose orbits we've mischaracterized as purely gravitational might also be far larger than we realize. As Farnokia noted, continuous monitoring of near-Earth objects remains critical, not only for understanding how these bodies evolve, but also for improving planetary defense efforts by identifying potential Earth impact risks more accurately. Every object we misclassify as an asteroid when it's actually a comet is an object whose future position we might be predicting incorrectly. And when it comes to planetary defense, incorrect predictions are exactly what we can't afford. I'll bring you the next update the moment any new peer-reviewed research identifies additional dark comets in our solar system, or if any new observations reveal more about how common these hidden objects actually are. If you want deep space discoveries explained accurately, separating what's actually confirmed from what's still speculation, that's exactly what we do here every single time. Drop a comment and let me know what part of this surprised you most. The fact that an object can fool astronomers for 28 years. The 19 standard deviation orbital deviation, or the implications this has for planetary defense. Like, subscribe, and turn on notifications so you don't miss the next update on this object. And I'll see you in the next one.